It's time to level up your skills in UMAT and VUMAT subroutines. In this video, we'll show you how to use these subroutines in non-isothermal elasticity, damage initiation, and progressive damage based on puck failure criterion of composite material, and other things, all with UMAT and VUMAT subroutines. So, be with us till the end.
In this first workshop, we will implement temperature-dependent elastic behavior using UMAT subroutine writing. First, their equations are presented. As you can see, the stress equation, contrary to what was stated in the elementary training packages, is temperature-dependent despite the similarity only in mechanical properties such as lambda and mu that are temperature dependent. Note that this time the elastic strain for each component is equal to the total strain minus the strain due to temperature changes. Therefore, we see temperature-dependent term in stress and strain equations compared to previous basic stress-strain relations. When we want to obtain the stress by subroutine UMAT in each increment, we have to add the stress in the previous increment with the stress changes in the new increment. Contrary to the temperature-independent elastic behavior of materials, stress changes will be different here. So, writing delta equation for stress, the first part of the relationship is exactly the same as non-temperature dependent elastic equation of materials, and the second part shows changes in temperature-dependent mechanical properties. In addition, unlike the first part, there are no strain changes in the second part, but the strain itself is seen, and the changes are only for mechanical properties. We have above mentioned formulas for mu and lambda. To write a temperature-dependent elastic model, suppose that the elastic strain at temperature T1 is equal to E1. And at temperature T2 is equal to E2, and the behavior between them is linear. Thus, by calculating the slope of the line, you can have other parameters such as strain or elastic modulus. By having the slope of the line at a point like it, T1 and E1, the relationship between the mechanical properties of the material in terms of temperature can be obtained. For example, for the elastic modulus, the following relation can be written. If we consider its coefficients of F0 and F1 respectively, it will help us in subroutine writing. We simulate our cube model with L side dimension. The required coefficients and values are presented here. Note that the force displacement is in the z direction equals to -4. You can also see the intended coordinate system here. Here, the behavior of the material at two temperatures of 273 and 700 K is considered, which Young's modulus is 200 and 150 gigapascal respectively. In the following, we discuss how to write subroutine according to the relations and then implement it in the Abacus software. From the viewport section, we can view the results simultaneously. For example, for the Abacus model and the subroutine model, we can compare the Mises stress simultaneously and see similar results. And the temperature we used to specify are now exactly the same. Each of the parameters we stored in SDVs, such as the elastic strains for subroutine at SDV1 to SDV6, can be seen. And after that, 7 to 12 other cases can be seen. So, as you can see, with respect to the stress contour and temperature contour, it shows the same value for both analyses. The analysis is done quite correctly. We repeat this for a large number of elements. Here we go to the mesh module and set it to a Bacchus high model with a large number of elements, and this is also done for the subroutine. You can see the results in job 5 and job 6. If we want to see the elements as well, we have to activate option Exterior Edges from here. You see, one is related to a Bacchus and the other is related to subroutine. We will have exactly the same results for both analyses, and other things can be observed and compared, such as a strain. Let's go for workshop number 2. In this workshop, we will talk about UMAT subroutine for damage initiation and damage progression based on puck failure criterion in 3D continuum elements for composite materials. You can see elastic equations for composite materials here that is also can be found in a Bacchus documentation. In this equation, stiffness matrix is 6 by 6, and stress and strain vectors each has 6 matrix components. In puck equations, first I want to talk about how to identify the initiation of fracture in composite fiber. During fracture in fiber, because the stress in one direction is parallel to fiber direction, damage initiation defines by this equation. That it has 2 terms for each tension and compression. It's notable that m sigma f is magnification coefficient, and the F index is fiber mechanical properties. Because the element type is shell here, we have local buckling caused by pressure due to compression stresses around hole. However, we can reduce scale factor here, but shell type elements affect the results anyway. However, if we compare the results, you see they are almost similar. Well, to sum up, we compared the results in shell and 3D continuum in different analyses. In standard 3D continuum, the stress is equal to 665 in compression type in X direction. And as you see, the stress in puck criterion is similar to 3D continuum. And as you see, the results between the shell type in abacus and 3D continuum in POC criterion are completely similar. And we did analysis in progressive mode. Also, in other packages, we have progressive gradual type. That is based on energy criterion, and the property reduction is based on hashing criterion for VUMAT subroutine. Thanks for watching. Bye. Hello guys, in this workshop we are implementing progressive damage for CZM cohesive zone model by UMAT. Pay attention here, traction equations in the cohesive element are in accordance with these equations. In this equation, Tn, Ts, Tt are normal stress, shear stress in the first direction and shear stress in the second direction, respectively. And K is a stiffness matrix. Epsilon n equals to separation divided on thickness. Shear strain is calculated based on these equations. If we want to determine the initiation damage of the cohesive element, the damage will start when this equation equals to 1. This quadratic equation is one of the equations used at the onset of damage in cohesive element. When we reach this point, we'll have softening after that. As mentioned, the identification of this point will be done by this equation. The softening will be presented by these equations. Traction will decrease based on the damage that will be happening. The value of damage is calculated based on this equation. Delta NF is the final value of separation, and it is problem inputs. Here we can see changes. Note that the solution pace is different for two analyses. In subroutine model, we see more progress. To compare, once in the perfectly elastic region and again in the maximum solved increment in abacus, we compare the results of subroutine model and abacus model. In this case, we check quads CRT when the value isn't equal to 1 yet. Use Create Display Group in such a way that only the cohesive will be visible. Select Cohesive. This moment is 0.58. And also in subroutine, we try to observe that moment for cohesive 0.58. As you know, if we want to see the damage criterion, damage initiation criterion actually is state V4. So we can compare state V4 here. As you see, the results and contour type should almost the same results obtained from abacus. Well, you can also compare the stress. Stress is shown in the abacus model as S. And use S33 to see the cohesive, which is normal stress. As for subroutine, we know that stress 1 actually is a stress N, so we use state V9 for the final output. As you can see, the results and the type of contour in subroutine and abacus are completely similar to each other. The maximum stress for abacus model is in 0.6750, and we set the results for subroutine to 0.67, and we will find 0.67. Yes, here is 0.67. If we check the damage initiation and its contours, we'll see an abacus and subroutine. The answers and the contours are almost the same. Also, if we want to see the value of damage progress, we use SDEG in the abacus model, which it will be a contour. And for subroutine state V5 actually is damage parameter. So we use it. When we use a state V5, again we will see the same answer compared to the result of abacus. These results show that the subroutine was written correctly and compared correctly. I hope you have enjoyed and got your results correctly too.
Hello guys! In this workshop we simulate kinematic, hardening, plasticity by writing the UMAT subroutine. Pay attention, in kinematic hardening behavior, yield surface will shift. In isotropic hardening, the yield surface will be larger. But for kinematic hardening, yield surface just will translate. You can see the displacement value here, which is x. First, it has initial surface and then it changes. If we want to rewrite the stress equations for this new state, first we should check original equation, which was in the elastic region. Difference equation will be according to equation 2, which strain difference are added to the equation. Equation of yield surface will be equation 3, that alpha is actually back stresses, which alpha will be equal to the value of yield surface transition, and S is the deviatory distress tensor, and sigma y actually is yield stress. Differentiation rate of equivalent plastic strain equals to equation 4.
As you can see, the results are completely similar. We can make this comparison for each case. Therefore, the analysis is done correctly. It is possible to do this comparison for multi-element models, as you can see here. We can also have the value of internal energy and dissipation energy. Internal energy for abacus is like this. And also plastic dissipation. We call these results on subroutine model as well. And also for the internal energy in the subroutine model. If we want to compare the results of the two models, here we will have the internal energy in the subroutine model and here for abacus model. When we draw both curves, we see the results will match exactly. So our calculations for internal energy are done correctly. In order for this comparison to be fully visible, we use two different colors to draw the diagram. We see that the results are exactly on top of each other. If we do this comparison for the dissipative energy in the two models of abacus and subroutine, we'll see that results are the same as previous mode, which in the initial step, when it's elastic mode, it's 0. And after we go to the plastic state, it shows its difference: brown for abacus and green for subroutine. Thank you for your attention. Hi! In this session, we will talk about writing VUMAT Subroutine for damage initiation and hardening based on Johnson-Cook model. As you see, stress-strain behavior has three parts: elastic behavior, that is until sigma 0, plastic behavior, that is until the point where D is equal to 0, and damage behavior. In this example, we will talk about the first two parts. The elastic region is definite, and in plastic region, yield stress and damage initiation are based on Johnson-Cook criterion. This is reduced Johnson-Cook equation that is used for calculating yield stress. It has a thermal coefficient, and because the abacus considers a big value for transition angle, we will enter large value in subroutine to compare the results with abacus. I will talk about it more in the software. Damage initiation index will be calculated based on equivalent plastic strain. Here we calculate epsilon. And when the summation of the differences of equivalent plastic strain over the damaged plastic strain gets into 1 or over it, damage initiation occurs. Here we have the explanation of parameters such as equivalent plastic strain at damage initiation or empirical material parameters. Stress triaxiality, that is pressure stress over the Mises equivalent stress. Here you can see the results. If you want to see both of them simultaneously, from Report, select Create and choose Tile vertically. One of them is abacus and the other is VUMAT Subroutine. As you see, the stress contour is almost similar. And the differences are because of calculation errors. For example, to compare contours from Create Display Group, Part Instance, choose Billet and select Replace and do it for other model. You can see stress results that are almost similar together. And also SDV1, that is equivalent plastic strain. And you can see Johnson-Cook damage criterion that it is SDV2 for subroutine model. As you see, the results are the same. You can see these are defined in state variables in subroutine. We can also compare energies from results, field output, choose internal energy and plastic dissipation for VUMAT model. And also we can do this for a Bacchus model. To compare it better, we can plot them in one viewport. For internal energy, the results are exactly the same. And also for plastic dissipation, the results are similar together. It showed that the subroutine is almost correct. In this workshop, I teach you how to write VUMAT subroutine based on Johnson-Cook plasticity, hardening, and damage initiation. It should be mentioned, this model includes damage evolution based on energy dissipated during the damage process. Stress-strain equation in this material model is based on the shown figure. To simulate progressive damage, it is necessary to calculate damage parameter. In damage initiation, damage parameter is 0 and it is accrued in this point. This parameter is calculated based on equation 1. This parameter is function of characteristic element length, effective plastic strain, and effective plastic displacement at the point of failure. Equivalent plastic displacement at failure is computed as equation number 2. After damage parameter calculation based on equation 1, effective stress can be calculated based on equation number 3. More information about different methods to calculate damage parameter is available in a Bacchus documentation. Note that damage variable reduced linearly. It could be changed exponentially or etc. You can see the results of two models parallelly and comparison different variables between both. As you can see, the stress magnitudes and contours are same for two models. Equivalent plastic strain for both models are same. In addition, contour and magnitude of damage parameter for both models are the same. It is the difference part between this workshop and previous one. Note that some parameters like solution state variables number 9 only available in subroutine model. And it is the advantage of using the subroutine which you can have any variables during other calculations. In conclusion, with these verifications, we can say that the subroutine has been written correctly. I hope you have used this workshop enough.
Hello everybody and welcome to our new video training package of Abacus. Advanced UMAT Subroutine, VUMAT Subroutine, Abacus, UMAT Tutorial. This package includes these sections. Workshop 1. Writing UMAT Subroutine for Non-Isothermal Elasticity. Workshop 2. Writing UMAT Subroutine for damage initiation and progressive damage based on puck failure criterion of composite material. Workshop 3. Gradual progressive damage for CZM or cohesive zone model with UMAT Subroutine. Workshop 4. Writing UMAT Subroutine for kinematic hardening, plasticity. Workshop 5. Writing VUMAT Subroutine for Johnson, Cook plasticity and damage initiation. Workshop 6. Writing UMAT Subroutine for Johnson Cook, progressive damage. Thank you for taking the time to watch this video. We hope it will be useful for you.